Hello, good afternoon everyone. I welcome all of you to YouTube channel of Gradeup. All of you please join together as we have discussed and we have committed. Now the session for the BARC has been started from today. We'll start from first of all our structural analysis. So all of you please join together. Am I audible to all of you? Hello Samajit. Good afternoon. Hello Atulya. So BARC, as you know, hello Julie, good afternoon. Please share it, and we'll start very soon, isn't it? We'll start very soon. Okay. Share it at few places so that people will come to know. Then we'll start very soon. Okay. So I hope all of you are doing good and staying safe. See, as I told you, if you'll see the question paper of the bar, although it is not available at all, but yes, from the students, those who did who sit for the examination. Oh, nice poster, thank you very much. Thank you. Nice poster with nice teacher, or nice poster with okay. So the students, those who were there, those who have already got experience of writing examination, if you'll ask them, the questions from the structural analysis part is going to come, and understand it. They cannot ask you the lengthy questions, as they have only 120 minutes 120 minutes for 100 questions, right? That is also very important point. So you need to prepare accordingly. So I hope I'm audible to all of you. My voice is audible to all of you. So let us start doing that. This is my small introduction. Those who are new can join my channel, that is Telegram channel, and you can also follow me on a Gradeup app. So the Telegram channel you can join, that is Civil by Ansari Sir. And after that there is one more line has been given by people, that is the surgeon. Now this is my a brief introduction, right? And then there are batches going on for gate, that is vision batch, and gate and es vision 2022 for English and Hindi, and both in English Hindi, right? All of you can join, those who are interested, and go for the subscription, right? Then for the BARC, enrollment has been started for the courses in electrical, electronics and mechanical, where 120 plus live classes will be there, and 10 plus subject wise formula notes will be there, and 7 plus mock test will be present. So for that also you can contact at this number those who are preparing for the BARC examination. Now first of all, let us continue with the indeterminacy. See, this part I will tell you this part. From the structural analysis, be ready with little bit of Truss problem, that zero member forces. Then what? The determinacy. Then what? That ILD portion, right? At least three portions, and including arches also came last time. So very easy problem of the three hinge arches must be you need to practice it. So all of you just practice accordingly. It will be very much convenient and easy to grab the marks. Can you tell me what will be the static intensity of the beam as shown in figure? What will be the static indeterminacy of the beam as shown in figure? I'm not getting any comments here. Meanwhile, do not forget to like and share. Yes, good afternoon, Shubham. So here I got only one answer. Several times I told you, whenever you are going for the indeterminacy or determinacy for static indeterminacy for beam, do not search it out for the internal one. See, although you have internal arrangement, several times I told you, do not go for any internal arrangement, do not see it, do not get worried about it, only go for the external unknowns. What are the external unknowns you have? The general external unknowns for the fixed one, you will be getting how much? 3 plus 3 6. Now 6 are the unknowns. I'll write it down, that unknowns are 6. What are the equations available to you? So I generally used to write down useful equation or available equation. Useful or available equation. So anyone is okay. You can write down available equation. In general situation, what are the available equations you have which you can utilize? So if you see that carefully, it is a 2D structure. So 3 equilibrium conditions, that is summation of fx equal to 0, summation of fy equal to 0, and summation of moment at any point must be equal to 0. That 3 will be there. Along with that, you will be having which one? The bending moment at hinge must be equal to 0. And what else? Here you will be having bending moment at hinge equals to 0, and due to this sliding action, the axial force, summation of the axial force also must be equal to 0. Summation of the axial force here must be equal to 0. Now, what are the equations you have? That is 1 plus 1 plus 1, that is total 3 equations you have there. So what is the actually unknown you have? Now unknown will be 0. So it is actually statically determinate one. Statically determinate beam. Determinate. Did you get that? Now next one. What is the static indeterminacy of the beam as shown in figure? What is the static indeterminacy of the beam as shown in figure? Can you tell me? Oh, is it visible, that figure? The diagram, is it visible to all of you? Not exactly, right? Do I need to change the position of that? Is it visible now? I think now it is. Now it is. Isn't it? So these two locations are hinge positions, right? These two locations are hinge position. What will be the static indeterminacy for this beam? Yes, you are saying it. See, let us see. As I told you, do not worry at all for any of the internal. See, this is not internal one, but this one is your internal arrangement. This one is totally your internal arrangement. Do not worry about it. It is actually a link. Okay. Now what are the unknown? What are the reactions you will be getting at the support? So here you will be getting maximum 3. Here it is a roller, you will get only 1. Here it is also a roller where you will get only 1. So total number of unknowns you have 3 plus 1 plus 1, that is 5. So unknowns I'll write down. Unknowns are 5. What are the available equations you have? Now available equations. What are the available equations you have? 3 equilibrium equations plus 3 equilibrium equations. Then one bending moment at this point must be equal to 0. Another bending moment at this point must be equal to 0. That is 2 equations you have available here. So that's how you have. Bending moment at this joint must be equal to 0 and bending moment at this joint must be equal to 0. Isn't it? So here also, fortunately, you can see that you have a 0. That static indeterminacy is once again 0, and it is a determinate beam. It is your determinate beam. Did you get that? I can see, Babu, you have deleted your answers. You have deleted your answers. Huh? Are you forget? See, these simple things only. Right? During the time of examination, when you are preparing, no, you will get confused. So sometimes take care of it. Here in this particular figure, please try to understand, this is your string attached to this. This is your string, or should I say it is a wire. It is a wire or string. Now what will be the static indeterminacy for this beam? What will be the static indeterminacy for this beam? Gate BM coaching. What is that gate BM coaching means? I didn't get your question. What will be the answer for this one? Okay. Gate BM coaching means gate bending moment coaching. What is that? Gate bending moment coaching? No, I'm not joking. I really didn't get that. Can you write down once again what exactly you're asking? So what is the static intensity for this beam? So can you see that there will be only one, if it is a string, there will be one only unknown here at this position. Then due to the roller support, you will be having one unknown at this location, that is one reaction, and you will be having a total 3 reactions here. So total unknowns are how much? Total unknowns, what are the total unknowns here? Total unknowns are 3 plus 1 plus 1, that is 5. What are the available equations? So equations, how many equations now you will be having here? So equations, if you will find out, 3 static equilibrium equation, 3 static equilibrium equation, then 3 equations from the equilibrium condition, and then the bending moment at this location must be equal to 0. That's all, 3 plus 1. So statically indeterminate to 1 degree. Statically indeterminate to 1 degree. That's correct. That's correct now. Ambati is there. How are you, Ambati? Doing good? Is it visible, this diagram? What will be the static intensity for this beam as shown in figure? Sorry, for this frame. For this frame. How to do that? See, for any of the frame, if you remember what I told you, those who are new, remember only one thing. What is that? What is that? Degree of static intensity for frame. For frame. Remember it. Remember it for frame. Do it very quickly. What is that formula? Can you tell me? Degree of static intensity is nothing but 3c minus r dash. Well, what is c here? C is number of cut. Number of cut which you are providing to make the frame. To make the frame. What type of frame you want to make? What type of frame you want to make? Write down. Open, stable, cantilever structure. That's all. That's all. You are trying to make open, stable and cantilever structure, isn't it? So number of cut, whatever you are going to provide to make that. Acha, you know already what is the meaning of cantilever. The cantilever means what? Whatever your structure, if you have only one support, is your cantilever, and you know that the cantilever is a determinate one, isn't it? It is a determinate one. Now how many cuts you need to provide it here? Suppose I'm providing one cut here, and what is this representation? This is a representation of roller support. This is a representation of roller support. Now cut it. This portion is completely stable. After cutting that portion, if you separately, if you take it out, this is 100% stable. You do not need to apply any of the force here, as the base is fixed. As the base is fixed, you don't need to apply. No need to apply any of the force here. So that's all. What about the right side portion? I will draw it once again. I'll draw it once again, the right side portion. For the right side portion, if you see, so of course I'm not going to draw the rest of that. Now can you see that? Is it a stable one? Remember it, we are trying to make always open stable cantilever structure. Now the member, if I'll provide name, that is maybe BC, member BC can slide over here, over this roller support. It can slide over here, so that sliding action should be stopped. So one force to stop the translation of this member is required to make it stable, isn't it? In fact, I should draw it completely. Wait, I thought that I'll not draw it. Let it be. Let it be. And then what? One translation has been stopped by providing one's force here. One moment must be provided so that your beam cannot rotate about this joint. So one moment is needed here. total two forces if you'll provide, now you can say that it is a cantilever and stable too. It is a cantilever, open and stable too. Did you get that? So that is the meaning of R dash. R dash is number of forces. I'll write it down here. What is the meaning of R dash? R dash is nothing but forces required to make same open stable cantilever structure. That's all. Or should I say forces, this R dash is required to make stable structure, stable cantilever structure. Right? Now how much you will get here? DS is nothing but how many cut you have given? Only one cut. Minus R dash. How many R dash you have? 2. So it is 1. So answer will be D. You all are correct. What is the kinematic indeterminacy for this beam, for this frame as shown in figure? What is the kinematic indeterminacy for this frame as shown in figure? How will do that? How to get the kinematic indeterminacy? How much kinematic indeterminacy will be there? How you are calculating it? Always remember, it is the degree of freedom at a joint. It is a degree of freedom at a joint. Now check it out. Check it out. The degree of freedom at a joint. Okay. Okay, let us check it out. See, here the degree of freedom is 3 at any rigid joint. Remember, at any rigid joint will be having 3 degree of freedom. What does it mean? Maybe due to any of the loading, you can expect that the joint can rotate. The joint can rotate, the rotation is there, then it can translate in X direction as well as it can translate in Y direction. So movement of the joint can happen either in X or Y, or it can rotate about the axis, right? So translation and rotation, all the 3 degree of freedom is possible at the rigid joint here. Here also you have a 3 degree of freedom at a joint. Now here it is a fixed, so 0 degree of freedom. It is fixed, 0 degree of freedom. Now what is the degree of freedom at this internal arrangement? That is very interesting to see. Very interesting to see. Now the degree of freedom at internal arrangements, if you will see here carefully, try to see it very carefully and you will be able to get that. Draw the diagram accordingly, which will help you to get more understanding, isn't it? Now you tell me only, what are the degree of freedom you will expect it here? The thing is that if I'll give the name here, suppose this is B, this is C, I'll give the C dash because the joint is a single joint, right? For more understanding. Now BC if you're talking about, or a complete joint of this internal arrangement, see, if you are trying to pull it up, what will happen? The whole joint will be coming up together. Agree or not? One by one, you just do agree with me. The whole joint, see, this is, I'm not trying it completely, I have taken this, right? The whole joint will be coming up together. If you are pushing it down, the whole joint will be going down together. So a vertical movement will be a common one for all. For all means what? For C dash D and for BC. At a joint C, that C dash D and BC will be having a common movement in the vertical direction. Agree? So let us write it down. So a common movement is in the Y direction, that is Y. So I will write down delta Y maybe. Now if I'll try to make sure that BC if it is coming towards this side, that is translation. if BC is either coming this side or going towards that side, that is not going to harm anything, or that is not going to affect C dash D. So I can say that the translation at this joint for both the beam, that is BC and C dash D, will be having two different translations can be expected. Are you able to understand that? For BC can translate in his way, and C dash D can translate in his way. So two different translations. So delta for BC will be 1 and delta for C dash D will be 1. Agree or not? This I'm talking about translation. Maybe if I'll provide that, maybe X direction. This is translation in X direction. This is translation in Y direction. Or more appropriately, if I'll write down, that is delta X of BC, and this is delta X of C dash D. Did you get that? Now, a rotation of C dash D is possible here, and whenever this rotation is going to happen at C dash D, whenever there is a rotation is going to happen at C dash D, it is not going to affect this another member. So C dash D can rotate according to his choice. C dash D can rotate according to his choice, and BC can rotate according to him. So now a different rotation is also possible. A different type of rotation is also possible. Can you see that? I'll just draw the line diagram for this guy. Suppose a BC is now getting bent, so there is a rotation. There is a rotation for the member BC, but you can keep that C dash D as you want. You can keep it as a horizontal, not required. He is not forced to rotate along with BC. He is not forced to rotate along with BC. That C dash D, if you want to keep it horizontal, it will be because it has an opportunity. It is hinge at this location. Are you able to understand this? So at two different rotation also you will be getting at this location, two different rotations. So that is theta for BC and theta for C dash D. How many degree of freedom at this internal arrangement you have now? Total degree of freedom at this internal arrangement is nothing but how much? 5. Write it down here. Total 5 plus 3, 8. 8 plus 3, 11. Now they have not given anything whether the members are inextensible or extensible. Simply subtract 1, 2, 3, 4. 4 member you subtract from 11. 11 minus 4, and you'll get how much? 7. That's all. That is the correct answer for this one. Did you get that? Five? How it is 5? 3, 6, 5, 11, 11 में से गया 1, 2, 3, 4, 7. No? How you are getting 5? He's asking kinematic indeterminacy, right? He's asking kinematic indeterminacy. So it means you need to work out. Huh? Did you get that? Okay. Let us move to another question. Figure. What is the static indeterminacy here? What is the static indeterminacy here? Is it visible now? Okay. What is the static indeterminacy here? What you'll do here? See, the way I told you, for a 2D structure, always remember the static indeterminacy is nothing but 3c minus r dash. And this is for 2D. This is 3D, right? For a 3D, remember it is 6c minus r dash. That's all. This is for 3D. 6c minus r dash. Right? Now do the same procedure. And you'll get the answer very, very easily. This position you consider it is a hinge. It is what? Hinge. This is a hinge here at this location. And consider this one as a, what you are going to consider? Consider it as a roller. It will be more convenient, more, not convenient, but it will become a little bit slightly tough. So you consider it as a ruler. It is not hinge, it is, you consider that as a roller. Now you tell me, if it is a roller one, what will be the static indeterminacy for this one? What will be the static indeterminacy for this one? Can you calculate that? Okay, I got one answer. Try it. This is fixed. This leg is fixed. Here it is fixed. See, try to understand first of all, how many cuts you need to provide. How many cuts you need to provide it here? 1, 2, 3, 4. Now analyze one by one. See, this one, if you see carefully, this is completely stable, isn't it? Because it has a rigid joint here, no instability at this beam or at this portion of the frame. At this portion of the frame, it does not have any instability. It is completely stable, this guy. Are you able to understand that? It is completely stable, isn't it? So first of all, ds, you got it 6 into total number of cut 4. But r dash now you have to calculate. You need to calculate the r dash. Now see, we will talk about this one where internal hinge is provided. So if the internal hinge is provided, try to understand that. If the internal hinge is provided at this location, what does it mean? There is an internal hinge here. It's a kind of ball socket joint. Have you seen that ball socket joint? It is your socket and there is a ball inside with a rod. Now you tell me, have you seen that? In a ball socket joint in a 3D, it can rotate in all the 3-degree axis. It can rotate in all the 3 axes, right? About all the three axes. It can rotate in the plane. If you see that, it can move due to the rotation, it can move in the plane, and it can rotate about its own axis also. It can rotate about its own axis also. So now 3 rotations are possible for one member. Are you able to understand that? 3 rotations are possible for one member. If 3 rotations are possible for one member, it is your hinge one. So 3 rotations means you need to stop the rotation of this guy. See, the bottom guy is already fixed at the fixed support. Now these two are unstable. You require 3 moments to stop the 3 rotation of this member, then 3 moments to stop the rotation of this member. Are you able to understand that? They are not a rigid joint. Both of them can independently rotate. Both of them can independently rotate. You can understand from the 2D structure also. Suppose you are providing a kind of two connections you can provide at one support, at hinge one support you can provide. This is just I'm just providing you with the support. See, 2 members can be provided at one support. That can be done. So both of them will be having independent rotation or internal hinge also. If you want to see, suppose you have a one member and it is at hinge here, one member. Another 2 member can be attached in such a way. Another 2 members can be attached. It can be pinned together. All the 3 can be pinned together in such a way that, now suppose if I'm saying that this is fixed here, but these 2 members can rotate independently at this location. So 2 moments will be required to stop the rotation of these 2 members. Similarly, here 3 plus 3. Total 6 forces will be required to make it stable. Did you get that? Total 6 forces will be required. That is 6 moments will be required to stop the rotation of these 2 members. Now what about this guy? We can see it here only. What about this guy? Here they are actually stable. This is a rigid joint, but the problem is that at a support it is a hinge. Hinge once again is a kind of ball socket joint. So first of all you need to stop the rotation of this member, which is 3 rotations are possible about a hinge. All the 3 forces will be required to stop the rotation. What about the backward? That side, right side backward, this one. What will happen to this guy? This part of the frame. Here you have a hinge. So 3 rotations must be stopped first of all. 3 rotations must be stopped first of all. And in a 3D, in a 3D, if you see what is a roller, you will understand. Suppose this is your surface. Over the surface, if you want to keep the roller, how does it look like? It will look like this, and it will be having wheels which will allow to translate. Now here you have a ball socket joint and the member, and you have a member and a member. This member can rotate about this hinge about all three axes, and the whole structure, the whole that support can translate both axes, that x and y. Only about the axis which is normal to the surface it will be able to provide the reaction. So the total degree of freedom, if you see here, 1, 2 and then 3, total 5 movements can be done here. All the 5 must be restrained here. So 3 movements must be stopped, and the 2 translation must be stopped. So total 5 translation or 5 movement must be stopped to make it stable, cantilever structure. So actually how many forces now you required? 6 here, 3 here and 5 here. How much? Total 14. So you'll get 10. Did you get that? Are you able to understand it? Now, what is the kinematic intensity of the space frame? What is the kinematic intensity of this space frame? Can you do that? Do not forget to like the session and to share the session. What will be the kinematic intensity of the space frame here? Okay, now if you see carefully, this is very simple. Now this is a truss, 3D truss, and you know that the kinematic indeterminacy for the truss, remember it always, for a 2D, the kinematic indeterminacy for the 2D, only the translation part has been considered. Rotation is a pure rotation, it is not due to bending. In any of the 2D truss, in a 2D truss also, all the joints will be having maximum 2 degree of freedom, that is translation either in x or y direction, that is translation in the plane, translation on the plane. And here in the space, if you'll see, the translation is the degree of freedom, if you'll count here, the rotational part we are avoiding because it is a pure rotation. So here if you'll see here, the two translation is possible here, that is it is kept on the surface, right? If it is kept on the surface, now only I told you, if the roller is kept on the surface, it can translate in both the direction. So 2 degree of freedom must be restrained here. Oh sorry, 2 degree of freedom is here. Then what? How many degree of freedom you have here? Total translation in x, y and z. All the 3 translations. So what is the total degree of freedom here? That is B. Did you get that? That's all. The kinematic indeterminacy for this 3D frame will be B, 5. Yes, another supports are hinge, but hinge will provide the rotation, and the pure rotation will not be we are not going to count that pure rotation. Now what is the kinematic indeterminacy for the continuous beam as shown in figure if the members are inextensible? Oh, that was not visible, I'm really sorry. Just a minute, I'll check it out, others one also. Meanwhile, just calculate, I'll check it out. I'll adjust all the figures then. Okay. The kinematic intensity here, see, here one rotation is possible. Here one rotation and one translation, that is 2 is possible. Here one rotation, one translation, that is 2 possible. And free end is also considered as a joint. So what is possibility? What is the possibility here? What are the possibilities here? Here 3 possibilities are there, isn't it? All the 3. X direction, Y direction and rotation. But as he is saying that it is inextensible, what will happen now? What will happen now? See, it can rotate, it cannot translate, it can only rotate. So only rotation here, only rotation here, only rotation here, and here a rotation and a vertical deflection both will be possible. Only the movement in the x direction will be restrained. Only the movement in the x direction will be restrained. So complete will be 1 plus 1 plus 3 plus 2, that is 5. That's all. Why 3? It will be 5, no? One rotation here, one rotation here, one rotation here, and two possibilities are there. 4 rotation and 1 delta y. That's all. Correct. Correct. Absolutely correct. Now, can you do this one? Inextensible means if the member cannot be extended. See, if this is the length of the member cannot be changed. Length of the member cannot be changed. I'm just saying that now you cannot change the length of the member. That's all. Inextensible. Did you get that? Which one is correct here? Indeterminate structures are economical and have a higher stiffness values. Extra restrained or member provides more stiffness. Also due to extra restraint at support, the bending moment reduces on the members and leads to less cross-sectional requirement. Which one is correct here? See, as he's saying that indeterminate structure, yesterday also I told you when people came to the free classes, see, if you consider only the 1, you will be able to answer it very easily. You have a simply supported beam and you have a fixed beam. Just compare these two. Compare these two. Same beam, same length of the beam, same UDL. Now this is one, first one is determinate, another one is indeterminate. Here what is the deflection? The maximum deflection you will have 5 by 384 WL4 by EI. And what is the maximum deflection here? You will be having WL4 by 384 EI. 5 times lesser than that. Then what? Maximum bending moment. How to draw the bending moment diagram? For this you will get WL square by 8 at the mid one. WL square by 8, isn't it? And for this one, when you are drawing it, you will get first of all a negative one due to the end moment, a negative one due to the end moment. Then what? A positive one due to the simply supported one, that is BD square by WL square by 8. And finally this middle portion will be overlapped and it will go away, and you will be having minus and plus. And if you see the value here, this height will be WL square by 24 almost, and here you will get WL square by 12, although this is negative. But nowhere you see that if you compare between these two, between determinate and indeterminate, the determinate is having maximum, see, maximum bending moment, just compare, it is having always more. So more bending moment, what it needs? More cross section, isn't it? More material to resist that bending moment. That is why it will become economical. Now one more thing, more bending moment is on determinate one, so more the area of the cross section will be required, so hence more money will be needed. So indeterminate is the economical one in that aspect. But at the same time, if you see here, the deflection is 5 times lesser than the determinate one. What does it mean? For the same loading, if the deflection is more in a determinate one and the deflection is less for the indeterminate one, I can say that it is more stiffer. Which one? The fixed beam is more stiffer than simply supported. So yes, indeterminate becomes more stiffer due to the restrained extra supports, extra restrained reactions. It will become more stiffer. So every point, if you see here from this particular example, you'll be able to understand that. So now you correlate this. Indeterminate structures are economical and have a higher stiffness. Yes, that's correct only. Extra restrained or member provides more stiffness also due to extra restraint to support. The bending moment reduces on the member and leads to less cross-sectional requirement. It is actually the explanation for that one. So yes, you all are right. A is the correct one. What is the static indeterminacy of the truss here? Is it visible? What is the static indeterminacy of the truss here? I think it was visible. What is the static indeterminacy for this truss here? It is very simple. For the truss, as I told you, the static intensity can be calculated as m plus r minus 2j. That's all. M plus r minus 2j. And here if you see m plus r minus 2j, how many members you have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Remember 10. Then in between do not count it 4. It is 11 and 12. 11 and 12. Until or unless people are not providing here an internal hinge, do not assume it. Do not think that there is an internal hinge. Generally it will be crossing each other. A single member will be crossing each other without any joint at that location, right? So 12 members you have. So 12 plus what is the number of reactions here? See, if you see carefully, you have a 2 reactions you'll be getting at this hinge support, 2 reactions you'll be getting at this hinge support, and 1 reaction you'll be getting at this roller support. So total number of unknown reactions are 5 actually. 5 here. Then minus 2j. What is the 2j here? Number of joints here. 1, 2, 3, 4, 5, 6, 7. So it is how much? How much you're getting? 3. That's all. Oh, you're getting C? How? How? That is what I have brought this question. See, 5 reactions. No, generally you used to put 3 here. That is the mistake you'll do. The reactions are not 3 here. Generally unknown reactions you used to put as a 3. So 12 plus 3 and directly you will add, you will do like this. Kitna ho jayega? 15 minus 7 14. So it will become 1. And you will mark this and you will become wrong. You will mark this one and it will become wrong. This is wrong. Did you get that? What is the kinematic indeterminacy for this truss? What is the kinematic indeterminacy for this truss? What is the kinematic indeterminacy for this truss? Yes. See, for the truss 2D truss, as I told you, each and every joint will be having maximum 2 degree of freedom, that is translation. No rotation will be counted here, right? And at the support also, see here 0 degree of freedom, no translation. Here there is one translation, rotation, do not count it. One translation, so I'll write down 1 degree of freedom here, 0 degree of freedom here. Then there is a joint here. So 2 plus 2 plus 2 plus 2. How many degree of freedom you have now? Kitna? 2, 4, 2, 6, 8, 9. 9, that's all. That's all. Yes, same truss, but it was a kinematic. Earlier I asked static. What is the static indeterminacy for this truss as shown here? What will do? Simply m plus r minus 2j. That's all. M plus r minus 2j. How many members you have? 1, 2, 3, 4, 5, 6, 7. 7 members plus how many number of unknowns here? 1, 2, and oh, you have to take care here. This is also a hinge one. This is not the roller one. So total four reactions are there. Do not get carried away with this same concept that you have only 3 reactions, 3 unknown. One can provide 3 to 4, 4 to 5. So how many joints you have? 1, 2, 3, 4, 5. Total number of joints 5 here. And finally, if you calculate such a you will get 1, isn't it? 1. That's all. That is the static indeterminacy for the truss. What is the kinematic indeterminacy for this frame? What is the kinematic indeterminacy for this frame? My favorite question, this one. Several times I have asked to you. Those who have seen, this is one of the favorite question. Because little bit here and there, we can do a little bit surgery here, isn't it? See, you calculate. For this I will give you the time. Don't worry. Okay, maybe you have done it. So see here, a kinematic intensity for the portal frame without we'll do the complete surgery for this one. If you have, remember, if you have any lateral support in between, you cannot go for a normal calculation. You need to check it out very carefully, or as this is a very simple one. No one will give you too much of complicated, otherwise who will check each and every joint? That is quite difficult. A normal portal frame, how many of degree of freedom you will be having? Total 3 here and 3 here, correct or not? Now if a lateral support will be provided, that too it is a roller, one, it means it is going to restrain the movement of this joint in x direction. Still I have a 3 degree of freedom here, but here the degree of freedom will get changed to only 2. Only 1 degree of freedom for this joint, that x movement in the x direction will be stopped. Agree or not? That is all based on, I'm not talking about whether the members are extensible or not extensible. That extensibility part I'm not dealing with, right? I'm assuming that all are extensible itself. Now based on that I will get the option here 5. Okay, I will mark it. 5 is the correct answer. Yes, you all are right. Here 5 will be the answer. 5 will be the correct answer. But remember, if for the same problem, please try to listen and watch it carefully. If members are inextensible, what will happen? If the members are inextensible, watch it carefully. If the members are inextensible, already the movement of, suppose if I'll give the name A and here B, already the horizontal movement of the B portion has been restricted by this roller. This roller is not going to allow the translation of joint B in the x direction. But it was supposed to move in the y direction. No one was stopping that. But here, as you are saying that if the members are inextensible, now what will happen? I'll give the name A, B and suppose CD. AD cannot move in vertical direction. So here earlier it was 3. Now 1 vertical movement will be stopped. Now A was actually moving in this direction. It was allowed to move, but as AB is inextensible, means AB cannot change the length. B is already stopped here. So by applying both situation, that is inextensibility and lateral support provided at B, ensures that no movement in x direction also for A. There is only one possibility, that is one rotation will be here at A. What is at B? B earlier it was having only the 2 degree of freedom when it was extensible. What was the degree of freedom? It was able to move in the y direction or vertical direction because it was extensible. Now I'm saying that it is inextensible. Now length of the BC cannot change. So now it will be stopped. Only the rotational part will be there. So only 1 degree of freedom will be available here, that is a rotational. So if it is inextensible, the kinematic indeterminacy for this frame will become only 2. Did you get that? So I hope you liked this session, and please do not forget to join once again. Tomorrow we'll see more and more problems. So at same time 3 p.m. But tomorrow will be a little bit faster. बी जॉइंट बी में 2 रोटेशन पॉसिबल है अगर मेंबर्स कनेक्टेड इंडिविजुअली. ओके ओके, yes yes, let us discuss that one also. You are now providing opportunity. Okay, you are saying that at joint B, see, actually it is a part of frame. So generally, until or unless the people are not saying that it is a part of frame. So part of frame means we consider it as a rigid joint. We consider it is a single rigid joint. Yes, you are absolutely correct. If the members are independent, both will be independent, then of course 2 rotations will be possible. Of course 2 rotations will be possible. You are absolutely correct. Did you get that? So please try to see once again. If you have any doubt, let me know. We'll be doing it a very more nice problems tomorrow, but little bit faster. Yes, Sudhanshu, once more means what is your doubt? You can tell me directly. Once more means a complete explanation. Once again, you can see on the video, and you can ask me in the Telegram channel if you have any doubt. That Civil by Ansari Sir is there. Civil by Ansari Sir. You can join there and ask me any doubt there. I'll share the PDF also. So be at 3 p.m. tomorrow. 3 p.m. tomorrow on YouTube. At 6 p.m. also I'm taking the classes. Today also there will be class for soil mechanics. At 6 p.m. on Gradeup app. Anyone, if it is needed, it's a basic one. Basic I'm conducting. Basic things I'm conducting on the app. So all of you can join. So that's all from my side. We'll meet once again tomorrow at 3 p.m. All of you please take care. Prepare well. And be ready for the tomorrow. A little bit faster session will be there. Little bit faster session will conduct. Thank you everyone. You're asking point A. Okay, we'll see tomorrow.